Gosh, I don't know why I always forget to do that. Okay, so instantaneous rate of change. So recall back from chapter 1, so back in the stuff we just got done, completing, but I think it's technically back from section 1 of 3. Oh, it's lagging already. Ooh, there we go. From chapter 1, the average rate of change between x equals a and x equals b for a function is going to be f of b minus f of a all over b minus a. So that's something we already know from 1.3, but just a reminder, because essentially we're going to take this idea and expand on it. So this chapter is we're going to be using this a lot, this section. So the first thing I want to do is I want to look at this example here. So we throw a grapefruit up in the air and we record the height of the grapefruit over a course of time. And we have this data here. So the first thing we're asked for is the average velocity between 0 and 1 and then 1 and 2. So we already know how to find that. So remember, the average velocity is exactly the average rate of change, just specifically in the context of position functions. So if we're going between 0 and 1, we've got 90 minus 6 over 1 minus 0. I'm going to breeze through this slightly because it's a topic we've talked about before, but as always, if you need to stop me, if you need me to go back over something, slow down, whatever, just let me know. So that would be our average rate of change between 0 and 1. It would be 84 feet per second. And then what about between 1 and 2? Well, so now we're changing, numbers just slightly. So we have 142 minus 90 over 2 minus 1. So here we're looking at 52 over 1, so 52 feet per second. But then what if I asked you, what is the actual velocity, the exact velocity at t equals 1? So I don't want to know, if you think about, remember, what these average rate of change are telling me is that between 0 and 1, on average, it's traveling at 84 feet per second. And then between 1 and 2, it's traveling on average at 52 feet per second. Well, what if I asked you, well, how fast is it traveling actually at 1? And so it's got to be somewhere between 84 and 52, or else these averages wouldn't be telling us correct things. So it must be somewhere between those two values, but where? So how might we be able to estimate that? Well, there's one way we could do it with the information we're given now, and then there's also something that could be more helpful if we could add on extra information. But for what we have right now, what we could do is we could average the two average rates of change. And for generality, I'm going to kind of put a kind of side note of one on each side. What I mean by that is I'm trying to look at x equals 1, t equals 1. And so if I can find an average rate of change essentially going in both directions, one between 0 and 1 and one between 1 and 2, I could average those two. So it's not just two random average rates of change, it's on each side of essentially the thing that I actually want to know about. So I could average those two average rates of change. I think that, I don't have it written in my notes, but I think that comes out to be something like 68. 84 plus 52 divided by 2 is, yeah, so this would get us 68 feet per second, in case you're just curious. It doesn't really matter, but that's what we would get. If we could have some more information, so if we had values closer to 1, that 1 looks really silly, but it's lagging super bad, so I gotta keep looking and slow down when it's not catching up to me. If we had values closer to 1, that would give us a better approximation, would give us a better. Like, say, for instance, someone added on to this table and told me this extra piece of data. and they were able to get it down to, you know, 1/1000th of a second difference. If I find the average rate of change between these two, what I would get is 68 feet per second, which in this case is coincidentally equal to the average of the two that I already had. That's not always going to be the case. In most cases, doing something like this is always going to be better. If you're able to take values closer to 1, that's always going to give you a better approximation than the average of the two. Sometimes in very specific situations, they might match or be very, very close to each other. But kind of this second option of if we have more information and we can get closer to 1, the thing we actually care about, we're going to want to do so. So that's kind of the idea that we're going to develop here, is we're going to try to be able to find an estimation for the exact velocity in this situation of exactly at a singular point. Now, we're not going to be able to find it exactly at this point in time. A few sections later, we're going to have some new rules come into our life that would allow us to find it exactly. But we're going to start off with this average rate of change idea to be able to estimate it. So now there's one thing that I have to talk about. To be able to do these two definitions, like it pulls on a word that we don't really cover in this class. So I don't know why it uses that verbiage for these definitions. That's how we define them, but if you're not going to talk about limits, then you should find a way around it. But anyway, what I mean is in a calculus course, and I know this is technically business calculus, but we don't go into as far depth as a regular calculus course. So in a regular calculus course, so not viewed completely in this class, there is a notion of something called a limit. Oh, lag. Let me try to unshare and reshare and see if that helps a little bit. Probably not, but just in case. So the notion of a limit. So a limit is going to approximate the behavior of a function near a certain point. Usually what that's going to mean is it's going to give you a y value that the function is approaching as the x values go to a certain value. What the heck do I mean by that? Let me show you a kind of picture off to the side. So again, we don't go into this in full detail at all, but we kind of need to understand the spirit of it, if you will, to be able to understand these next two definitions. So here's kind of the spirit behind the limit, if you will. So say I have some weird looking function. I mean, it doesn't even need to be a weird looking function. Actually, no, I was going to make this slightly different than last time. Let's do this and that. Sure. Yeah, let's go. It doesn't matter. And let's say that's 4 and this is 2. So the way I've drawn this very weird function, we don't actually have a point at x equals 2. That's why there's an open dot there. The function doesn't actually exist there. But what I can do is I can talk about the notion of a limit. Now, don't get freaked out by the notation, because again, we don't talk about this in full generality. This is just the notation you would use. So if I were to ask essentially the limit as x approaches 2, what that idea is we're looking to see what the function's doing as my x values approach 2. Because I'm not equal to anything at 2 because there's an open circle at that point, so I can't say what is f of 2 because that doesn't exist. But if I get really, really close to 2, kind of where am I on the graph, if you will? What's my y value looking like? Well, as I get obnoxiously close to 2, I'm essentially going to be up at a height of 4. So we would say that the limit here approaches or is equal to 4, because as I approach x equals 2, even if I don't actually get to x equals 2, I'm essentially up at a height of x equals 4. So the idea behind a limit, it's kind of like, when you're, 5 years old, and usually if we're in person for this class, I would actually go up to someone and do this awkwardly. But when you're 5 years old and you walk up to someone, you're like, you put your finger like really right next to their arm, and then you're like, I'm not touching you. And it's like funny because you're 5. That's kind of the spirit behind a limit, is you're getting obnoxiously close to something, but never actually getting there. And then the answer to that limit is essentially what, in most cases, it's what, sorry, my English has decided to break. in most cases, we're talking about y values, but it can be more than that. It can just be kind of, as you're getting closer and closer to that value, what is the thing you care about equaling, if that makes any sense. And hopefully, I have a diagram in a second, and hopefully that'll make a bit more sense. But that's kind of the idea, is we're making something as close to something else as possible without ever actually getting there. So I'm getting close to 2, but not actually being 2, if you will. So some definitions. So the instantaneous velocity, So the instantaneous velocity of an object at time t is defined to be the limit, which is why I needed to talk about it, of the average velocity of the object over shorter and shorter time intervals containing p. So essentially, we're going to find average velocities for something that's the thing we care about and something obnoxiously close to that value, which is why we bring in this idea of a limit, is we're taking the two values that we're using for the average velocity and making them as obnoxiously close to each other as possible. Now, just like with average velocity and average rate of change, there's also the generic form of instantaneous velocity, and that's going to be the instantaneous rate of change. Instantaneous rate of change. So just like with the average one, the velocity one is just specifically in that specific context of a distance function. So the instantaneous rate of change of f at a, also called the rate of change. So sometimes they essentially drop the word instantaneous and just say rate of change. So the rate of change of f at a is defined to be the limit of the average rates of change of f over shorter and shorter time intervals around a. Again, this idea that we're taking the two values in the average rate of change and making them as obnoxiously close to each other as possible. And let me kind of write that kind of down. So essentially what we're going to be doing, and actually I'm going to say this too. So to estimate, so again, right now we don't know how to find this exactly, so we're going to be estimating it. So to estimate the instantaneous, I'm going to abbreviate rate of change or else I'm going to run out of space. So to estimate the instantaneous rate of change, find the average rate of change for as small an interval as possible. And we'll do an example in a second after I draw the little picture I want to draw. I'm going to write this down. If it freaks you out, forget about it, but it might be helpful to someone, maybe. Or maybe it's just freak your friends out with scary math notation at parties. So say I write down something like this. Now, don't freak out. I know it looks really freaky, but got an x plus h here and an x plus h here. And an x here and an x here. This is just an average rate of change. I've just written the average rate of change where one of the values is x plus h and the other value is x. It's just an instantaneous, average rate of change. Officially, the official definition of an instantaneous rate of change would be saying we're taking the limit as h approaches 0 and it's lagging. Pop in there, limit. So the limit as h approaches 0, because that would be saying that if h is as close to 0 as possible, then x and x plus h are going to be obnoxiously close to each other because we're adding on something that's really, really close to 0. So that's kind of the official definition, if you want to know it. If you don't know it. But this kind of idea of taking the average rate of change, and my F didn't write correctly. 4. Average rate of change 4. as small of an interval as possible. This kind of idea is how we're going to be calculating it. So I want to draw a picture really quick, and then we'll look at some examples of what how we're actually going to calculate these. So I'm going to scroll down really quick. Now this says derivative, but that's because I'm getting ahead of myself. This also is for instantaneous rate of change. I should put this farther up in the notes, but too late now. So let's say I have a function. And I don't know, we got 1, 2, 3. And so say I want to talk about the instantaneous rate of change at 2. So instantaneous rate of change at x equals 2. Well, what that would be on this graph is it would kind of be this line right here. Well, it would be the slope of this line. So instantaneous rate of change at 2 is the slope of this line. And essentially what this line is doing is it's touching the graph in exactly 1 point at x equals 2. So it's not touching that graph in any more places than just 2. And the slope of that line would be the instantaneous rate of change. Now that's kind of why we can't calculate it exactly right now, because I don't know how to find that equation of the line because I don't know what other points are on that line. The only point I know that's on that line is at x equals 2. I don't know any of the other points that are on that line, so I can't find that slope exactly. So essentially what we're doing is, so say I take a break really quick and I draw, points at 1 and points at 3. So I'm going to come back to that idea of that. Well, this is unfortunate. Those look parallel. Pretend they don't look parallel. Or pretend you don't know how to, maybe you don't know anything about parallel lines, but if you know stuff about parallel lines, forget them. So essentially the slope of this line is the average rate of change between x equals 1 and x equals 3. So I could find that value because I have 2 points to use, and I could find the slope of that line. Apparently I drew this function so in such a way that I kind of screwed myself over, but it's going to be all right. Because now these lines aren't looking like how I wanted them to. But it's okay. You know what? I'm going to fix it by doing this. Dun, dun, dun. Let's pretend that point goes up just the tiniest bit more. I know it's kind of past 3, but to help illustrate what I need to illustrate, I kind of need them to differ a bit more. There we go. That looks better. So let me just move 3 over, and that'll just fix that. Sorry, as drawn, it was just not going to make as much sense as to why we couldn't take that. So now the red line doesn't look parallel to the green line, and that's good. So now we've got this blue line here. I know I've got tons of lines going everywhere. The slope of this line, I have a point. The slope of this line would be the average rate of change between x equals 1.5 and x equals 2.5. And now that I've redrawn it, you can kind of tell that the slope of the blue line is closer to the value of the slope of the green line than the slope of the red line was. So the closer I bring those points to x equals 2, the better the slopes are going to match, if that makes sense. So, and I really wish we were in class and I could be pointing at a board. So we started with, essentially imagine starting with these 2 red points, grabbing them and dragging them towards x equals 2. The closer I bring those 2 points to x equals 2, the better the slope of that line that I'm dragging, if you will, is going to match the green line that I actually want. So essentially what we're doing here is, since we can't find the slope of, the slope of the line that I actually care about, because I only know one point that's on that line, what we're going to do is we're going to find the slope of a line of 2 points obnoxiously close to the thing, because I need 2 points to find the slope of a line. So if I take something obnoxiously close to what I want, the slope of that line will be essentially good enough. Hopefully that makes sense. Does anyone have any questions about that idea before I go on to an actual calculating example? Okay. So let's actually calculate one of these instantaneous rates of change. Now I gotta scroll back over. Stop freaking out. There we go. So say we have that the quantity in milligrams of a drug in the blood at time t is given by Q equals 25, 0.8 to the t. Estimate the rate of change. So again, sometimes they don't use the word instantaneous. So estimate the rate of change of the quantity at t equals 3 and interpret your answer. So what we're going to do essentially is we want to estimate using the average rate of change at x equals 3. Why do you randomly zoom in? Stop doing that. And now you're not letting me zoom out. Zoom back out. Too far. And something really close to x equals 3. Because again, I can't find the slope at a single point, because to calculate a slope, I need 2 points. So I'm essentially going to use 3 and something obnoxiously close to 3. Now usually, so you're going to use 3. Sorry, these should be t values. Sorry. I should be using the correct variable. Erase. Oh, now my pen's freaking out. Virtual learning is so fun. Just kidding. I hate it. I'm not salty. Anyway. So we've got t equals 3, and then we're going to take something obnoxiously close to 3. Now by obnoxious, we're not going to go super crazy. Usually what I'll do, I usually default to just kind of tacking on an extra 0.001 to it. Some other acceptable values, you could use 3.01. This is about, I'm going to say this should be the lowest you go. I don't think lowest is the best word to use, but I can't think of a better one. What I mean by that is you should not use 3.1 unless you're specifically asked to do so, and I'll tell you in a second how you know whether you're asked to do that or not. Because when I say we want to get obnoxiously close, 3.1, while in some contexts is close, in this context is actually not close. So we at least want to take 3.01. Some other acceptable values is you can essentially go the opposite direction, if you will. So you could use 2.999 or 2.99 if you want. Again, 2.9, just 2.9 would probably be a bit too far off, but those are kind of pretty decent ones. In terms of Wiley, well, and just in general, sometimes they'll specify what they want you to change by, and they'll usually say something like let h be 0.001, which would tell you that you would want the value you care about and then the value you care about plus 0.001. So sometimes they'll say let h equal 0.01. If they say that you can let it be 0.1, then you can use something like 3.1. If they don't specify, you can technically choose, but again, you should choose something that's either tacking on 2 decimals or 3 decimals. I don't think they use this, but just in case, they might also say something like change in x, but usually it's presented as an h. But if they have, let h be blah, 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 or let change of x be blah, 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 That's essentially telling you the value you're adding, or you can subtract to the value that you care about. So, to the point, now we've actually got to find it. So we want to estimate the instantaneous rate of change. So we're going to use the average rate of change to do so. So we're essentially going to plug in 3.001 to the function, and then, whoops, and then plug in 3, and then divide by the change in x values, t values. So the function we're using here is the 25 times 0.8 to the t. So I'd essentially find 25 times 0.8 to the 3.001. Now here's the other thing about ones like this. Take a lot of decimal places. And then the other one, let me just get that piece really quick, 12.8. Take a lot of decimal places for the, I'll call it the weird calculation. Take kind of as many decimal places as you can. Technically, I dropped the last 2 that a calculator would pull up, but taking this many is enough. But just try to take as many as possible, because if you round too soon, especially for Wiley usually has a pretty decent tolerance for these. It's not like 1.5 where the notation is weird. It's just the tolerance of the numbers that it will accept. And if you round too soon, it could really mess some things up. So try to take as many decimal places as you can as you're going through it. And then at the end, if they ask you to round, do so then. So it essentially we would get negative 0.002856 divided by 0.001. We'd get negative 2.856 as our estimate for the instantaneous rate of change. Now these are technically slope values. So what would the units of this be? Well, it would be the units of essentially the Q values divided by the units of T. So we'd have milligrams per minute. Questions on how I found that before I interpret it? Okay. So I'm going to scroll back down really quick. These are all, everything we're talking about, instantaneous or average, are all slopes. So if I want to interpret this value, which is an estimation for an instantaneous rate of change, it's a slope. Well, we know how to interpret slopes. That was back in, that was probably 1-2, where I essentially gave us the 2 different ways we could write them. There was a rate way and then like a, kind of step way. Increase by X tells you how much you increase by Y. And I told you that it was going to come back to bite us in the butt. Here we are. So we want to interpret this, but since this is a slope, we'll use our interpretation for slopes. So I'm going to use the rate way for this specific example. So a reminder of the rate way, what we needed to do is we first needed to tell them essentially where we're starting at, which would be the t value. So what we'd want to say is we'd want to say after 3 minutes. So where are you starting? What's the starting value, the value you care about? And then you remind them what the y, quote unquote, y value context is, which in this case is the amount of the drug in the blood system. So after 3 minutes, I would phrase this, how would I phrase this? After 3 minutes, the quantity of the drug in the body, the quantity of the drug in the body. So now we've essentially set it up, and now we just need to essentially tell them what the slope value is. So since the slope value is negative, we're going to say is decreasing at a rate of 2.856 milligrams per minute. Whoop, ran out of space. That says minute at the bottom of that. Just got a little squished. So that was one of the 2 ways that we could interpret slopes. That was kind of our rate way. questions, concerns on that? Okay. This next definition, so the derivative of f at a, really super fancy f for function. The derivative of f at a, which is written like this, is the instantaneous rate of change of f at a point A. So essentially we're now saying we have the instantaneous rate of change. If I say the derivative of f, that's going to mean the exact same thing. Well, the derivative of f at a, I should say. The derivative at a point is the same thing as the instantaneous rate of change at that point. So they're equivalent definitions here. This little piece of notation here, we would read this as f prime of a. And let me get rid of the box. But that's how you would read that notation, f prime of a. So that means that essentially anytime we're asked to, well, again, at this point in time, we have to estimate. So at any time we're asked to estimate a derivative value, we use an instantaneous rate of change. Now, there's a kind of, so if we want the derivative at a, that's equivalent to the instantaneous rate of change at a, which we estimate with the average rate of change. So it's kind of this long kind of path we've got going on now. Now, I want to stress that the average rate of change is not equivalent to the instantaneous rate of change. We are using the idea of an average rate of change to estimate an instantaneous rate of change. But again, as I've said a couple times, we don't know exactly how to find those yet. We will eventually, but right now we've just got this estimation. That's the best we can do. So they're not the same thing. They're technically different. They're very similar, but they're different things. Okay, so say I want to estimate f prime of 2 if f of x equals x cubed. If you know derivative rules, you know we'll eventually be able to do that in about 2 seconds. But what we've got right now is we've got to use the average rate of change. So if I want to estimate f prime of 2, essentially I need to use 2, and I need to use something close to 2. So let me do 2 cases in this one. I'll calculate it with 2.001, and then I'll do it again just for giggles with 1.999. Because I also should make a clarification on something as well. So say I want to find the instantaneous rate of change at 2. So I'm going to estimate it using the average rate of change between 2 and 2.001. So we're going to have f of 2.001 minus f of 2 all over 2.001 minus 2 once it stops lagging. There we go. So then if I put 2.001 into my function x cubed, so 2.001 cubed, taking as many decimal places as I can, 0, 1, 2, 0, 0, 6. I am going to drop off the 0, 0, 1, but again, as long as you take, 6-ish, should be good. 2 cubed is 8, 2.001 minus 2. Wow, the lag. There we go. So, well, now I gotta wait for the lag and also pause so people can catch up. So if we go ahead and do that, we'll get 0.012006 divided by 0.001, which will be 12.006. If you know derivative rules, the actual answer, exact answer, is 12. So you could also argue, well, if you rounded sooner, then you would have got the actual value. I did that on purpose. I specifically made it so that I took enough decimal places to make it just the tiniest bit off. Because again, we should be taking as many decimal places as we can. You should not take that to mean if you round sooner, you'll get the exact answer. That's not what's happening. But say I then wanted to try the opposite way, if you will, the 1.999 instead of the 2.001. So let's do f of 2 minus f of 1.999 over 2 minus 1.999. You never have to do both unless they tell you to. I'm just doing both because I want to demonstrate something. Oh my goodness. Zoom back out. Why do you do this to me? There we go. So we've got 8 minus 7.988,006. Which would give us 0.01194 over 0.001. I get 11.94. If I took more decimal places, could have gotten 11.994 if I took all of the decimal places. Once it stopped lagging, come on. I could have gotten 11.994 if I had taken all of the decimal places with that 7.988 blah 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 blah. But I didn't. But it's okay. The point. These two aren't the same number. Obviously. They're different numbers. Depending on not only which direction you choose, if you will, if you add 0.001 or if you subtract 0.001, and also depending on, what H value you're taking. Are you just taking 0.01 or are you taking 0.001? Anyway, the point is, your answer is often going to differ from somebody else if they take a different value. They should come out to be relatively the same thing. Those are both obnoxiously close to 12. So like both of them would be considered correct unless they had specified one way and you didn't do that specified way. But both of those are correct. So don't panic if you're like doing this with somebody else and they're choosing different values than you and they're getting different values. That's going to happen. As long as you're doing the process right, you should be good. Which, again, also, just be really careful with the Wiley homework that's coming up next week. Just make sure to read their instructions. Make sure my words are getting jumbled. If they specify what value to use, make sure you use it. Take as many decimal places as you can. And if it's still being weird, just let me know. Again, it's not really a notation thing like last time, so I don't think it will be as bad. But as always, if Wiley's a jerk, just let me know. Questions, concerns on that one? All right. So I want to do kind of one more thing. We might not be able to get to the last example in this section, but it'll be all right. We'll do it on Monday. So I just want to stress one more time that these are slopes. And the instantaneous rate of change is specifically the slope of this line that only touches the graph in essentially exactly that one point. So that's kind of what we're going to use for this next one. We're going to be drawing these lines that essentially touch that point in pretty much just that one spot. Let me erase this to make that. There we go. So come on, scroll. Say we've got our graph of x squared here. And I want to determine whether the following values, I'm not going to be able to figure out what the value is, but we're going to look and see if it's either going to be positive, negative, or approximately 0. Again, we're not going to know what the actual number is, but we're going to be able to figure out whether it's one of those things. So let me pull out lots of colors here. So we got f prime of 1. So I'm going to go up to 1, and essentially I want to try to draw that line that just touches it here. Now, if that is confusing to you of what the line's going to look like, just take something that's kind of obnoxiously close to it and imagine drawing the line between those 2 points. You can do it that way. That's kind of like the estimating with the average rate of change kind of idea. You're taking something obnoxiously close to that point on the function and drawing a line between the 2 of those. So we've got this line here. Well, is the slope of that line positive, negative, or 0? And if we were in class, I would wait for someone to answer, but talking to a screen is weird. So that's going to be positive because that's an increasing line. It's going up from left to right. So that means the slope of that line is positive. Positive. Yeah, I spelled that right. So since the slope of that line is positive, this value f prime of 1, don't know what it is, but it's going to be positive. What about f prime of -1? Let's go over to -1. Take something obnoxiously close to it. Draw a line between those 2 points. Look at the slope of that line. Is the slope of that line positive, negative, or approximately 0? That line is decreasing, so it's negative. All right. Lagging. What about f prime of 2? Go up to the function at 2. Something obnoxiously close to it. Draw the line between the 2. Boink. Boink. Slope of that line, positive, negative, approximately 0. That's got a positive slope. So whatever value this is, it's going to turn out to be something positive. And green. What about f prime of 0? Go over to 0. Something obnoxiously close to it. Draw the line between those 2 points. So we've got a straight horizontal line here, which would have a slope of 0. So here we actually think that the value would be 0. Maybe it's not exactly 0. It is, but we don't quite know that yet. So we can say that it's probably going to be approximately 0 because the slope of that line we just drew, that's a horizontal line. So the slope of that line is going to be 0. Questions, concerns on that idea? Okay. So I want to do just this example 5. We won't get to example 6, but that'll get taken care of on Monday. But example 5 is kind of a similar idea here of positive, negative, or approximately 0. We've got to do a tiny bit of thinking on this one, though. So f prime of 1. We were just kind of looking at those. So that's the one where we take the line that's essentially touching the graph at just x equals 1. So we're going to go to x equals 1 and go up to the function, take something obnoxiously close to it. Whoop, that's bad. Draw the line between them. Now, maybe I should have been stressing this last. No, wait, I was. But anyway, because we want to just make sure we illustrate it graphically. It's the slope of this line. So it's not like that line in general. It's the slope of that line, which technically, I mean, I guess you could illustrate it with that little slope triangle, but the graph's going to get way too cluttered if I put that, so I'm not going to put it. I'm just going to put the word slope of this line. Well, what would the slope of that line be? Positive, negative, or approximately 0? That would be a positive value, whatever it is. Now this next one, you might not see it right off the bat. But think about, what we have once it stops lagging that makes something that looks like this. Like what calculation can we do that looks like this? Well, this essentially looks like an f of b minus an f of a all over b minus a. Well, that's an average rate of change. Well, that's another slope. So it's essentially going to be another slope, but it's the slope of what line? It's the slope of the line between the 2 points that you're looking at. So what this is going to represent on the graph is we're going to have a line between x equals 1 and x equals 3. Now if I draw the line between them and remind ourselves again that this is going to be the slope of this line, Well, is the slope of that line positive, negative, or approximately 0? We're going to get approximately 0 because that looks like it's a pretty straight line. Straight horizontal line, I should say. All lines are straight. Now, this last one is a bit different because it's not a slope. F prime of 1 is a slope. That's how it's defined to be. It's an instantaneous rate of change, which is a slope. The second one's a slope because it essentially looks exactly like a slope formula. But then this one is just taking two values and subtracting them. It's lagging a little bit. You got this. You can do it. I believe. Should I not believe? There we go. So we're just subtracting two values here. So it's not going to be a slope at all. So we don't need to draw a line. It's not considering a slope, but we are considering f of 2 versus f of 4. Well, if I wanted to kind of actually point out where this f of 4 minus f of 2 actually looks like on this graph, essentially what it's going to give us is kind of this distance here. So this distance right here, once my pen, goodness gracious, this distance right here is f of 4 minus f of 2. Kind of that change in y value, if you will. But then we need to be the tiniest bit careful, because is this positive, negative, or 0? Well, look at these y values on the graph. F of 4 is smaller, and f of 2 is the larger y value. So while it represents this distance that I just, kind of pointed out right there, it's actually going to turn out to be negative because we're taking a smaller value minus a larger value. So this would end up being negative. There we go. Once again, this last example, it's literally the last thing in 2.1. We didn't get to it, but it's all right. We'll do the last example on Monday, and then start 2.2. I think I'm going to do 2.2 the tiniest bit different, but I'm not entirely convinced yet. It might go horribly, so we'll see if I just change my mind and just go back to regular notes anyway. But if you don't have any questions, feel free to leave. Have a great weekend. See you on Monday. If you have some questions, feel free to stick around. I'll be here for a little bit. And yeah, have a good day.
I just want to. Do we have any homework Sunday night?
I meant to say that. No, since we had the exam this week, there was no homework this week. So there's nothing due on Monday. The next thing you're gonna see is what pops up on Monday, but there's nothing due this coming Monday. So no, you're good on that.
Okay, thank you. Have a good day.
Thanks, you too.